Okay, so just a few things I want to say. First of all, just for all the students who participated in yesterday's the labs yesterday, I sent to Shankar several files with mod files with the solutions to the problems, so that some of the solutions that we didn't have time to see all of them during the labs, you can then have them there. And also there was, for today's first set of problems for lecture 3, there were some typos in one of the mod files for the template, one called perm.mod, so that the corrected file for the template is also in the, together with the other files for mod in the repository for that. So just use that template instead of the one by copying and pasting from the LaTeX. So what I want to do today is to give, first of all, sort of a brief summary of where we are. We're in the middle of the course of 4 lectures. What you have already seen about mod in the first 2 lectures, and what the last 2 lectures that you already have looked at are about, and what the problems in the labs today will be about, regarding that. Somebody in the previous discussion on mod asked a very good question, which was, what were the design goals of mod? And my answer to that was that the main goal was that, since the intention is for mod to be a mathematically modeling language, which at the same is computational, it's also a programming language, but tries to make programming mathematical modeling, then we want to have a language that is as expressive as possible to represent systems, computational systems in it. And the first 2 lectures have been focusing on the functional subset, systems that are deterministic, that have a single result from some input or initial state, can always be described nicely in equational logic in a functional way. But mod wants to also express concurrent systems that may be highly non-deterministic and don't have this thing of having a unique solution. So concurrent systems like that. And so that's what the lectures 3 and 4 are about. And in lecture 3, one of the most natural things are concurrent object systems, where you have different objects that communicate with each other through message passing and things like that. And so then these lectures are about that. And once you have that, then we can also do some actual verification, system verification. And this is what lecture 4 is about, and that the second part of the labs today will also be about. How can you, once you have defined a mathematical model of your system, maybe a cloud-based transaction system or a communication protocol, a network protocol, a mutual exclusion protocol, things like that, how can you actually verify properties about it? And mod has a number of ways of doing that. Has a model checker for linear temporal logic, has a theorem prover for reachability logic for concurrent systems, different things like that. But in the course, we're going to be focusing mostly on invariance and how do you verify invariance. And I want to just have a whiteboard here. Let's see, I want to make sure you see the whole whiteboard. Can you see the whole whiteboard okay? Or shall I bring it a little closer, or how? Does it look okay?
That's fine for me. Okay,
so let me tell you how we can verify invariance in mod once you have specified the system as a system model, as a rewrite theory. So this is the set of all the states of your system, we begin in some initial state. And in blue, you have the set of reachable states, the states that are reachable from this initial state. And we would like to prove that this system from this initial state satisfies an invariant. So in red, I have described the set of states that satisfy the invariant. So if things go well, if the invariant is really true, then you can think of the red part as some kind of safety envelope inside of which the reachable states are contained. Now that invariant can be described very easily by the set of states such that some predicate on a state I of x is true. So
Jose, this is Warren. I'm still just getting, a 7x7 matrix of pictures, and so your picture of I can see your concentric rings, but I don't see very well your script, and so I'm wondering if you could project.
Warren, you can switch to speaker view. So go to the top right-hand corner.
Oh, okay. I'm sorry. Thank you.
Okay, sorry. Yeah. So the set of states satisfying in red will satisfy some predicate I of x. And I'm going to describe as bracket I the set of states defined by the predicate I. Okay, and then the complement in the set of states of that is the thing outside. So it will be the set of states minus the one satisfying the invariant will be the thing in the outside range, okay? And now how can you verify that in Maude? Well, very simply with the search command. So you give the command search init arrow star, which explores all the reachable states, and then give it a pattern, namely the variable, look for a state x such that the invariant is false. So then search is going to do breadth first search and keep exploring the set of reachable states. Now, two things can happen. If the set of reachable states is infinite, then of course the search will be forever, but if it is finite, then it will stop. And if it doesn't find a state like that, then it will be true that we have a situation like that. Now, suppose that the invariant is violated. Whether the number of states is reachable states finite or not, it doesn't matter. What does it mean the invariant is violated? It means, let me see. It means that it doesn't look like this, but it looks like that. But if it looks like that, then of course we will hit a point here and finite depth. So regardless of whether the number of reachable states is finite or not, by breadth first search, we are guaranteed that if the invariant is violated, we will find a counterexample. And so this is it. This is a general method to find violations of invariants, to verify invariance fully if the number of reachable states is finite. And the only remaining case is if the invariant is true and the number of reachable states is infinite, then you wait forever for an answer, but you can do bounded model checking by bounding the depth at which you're searching, and then you can at least have a verification of the invariant up to a certain depth bound. So we will see several examples of this in the lab today, but in some way we have been building up just the basic ideas about Maude, how to specify deterministic systems in equational logic in functional modules, and then how to specify concurrent systems by rewrite theories. So you have then the mathematical model of the system, which, as I explained in the lectures, there is a mathematical model in the sense of first order logic, defined by a mod module, either a functional module or a system module. If this is a functional module, is the canonical algebra of the functional module. If it is a system module, is a transition system. And then now for that mathematical model, we are now verifying, in the case of concurrent systems, the case of invariance by just the search command in mod. So that's what we will do in the lab. And as I said, there are many other forms of verification that you can do, both deductive and model checking ones. But in this course, we're focusing just on invariance, which are a very common safety property that one would like to verify, and for which just the search command in mod provides a model checker. So that's sort of, in some way, these are the main ideas that will be covered today. I'll be happy to further elaborate on them, explain more things, and answer any questions that you might have.
So yeah, I had the same question as Warren, Jose. So this is a kind of a search for a counterexample. You're starting from the initial states and searching for a counterexample. And there's this distinction between an invariant and an inductive invariant.
Oh yeah.
Could you actually do the dual thing of actually proving inductivity?
Yeah. So yes, so we can also we can do deductive verification to prove inductive invariance. And there are two tools that we have developed in the mod environment for deductive reasoning about that. One is called the invariant analyzer. And then the other one is called the reachability logic theorem prover, where we have verified substantial problems, like, for example, the security properties, including the same origin policy of the Illinois browser and operating system iOS browser. We verified it, using the reachability logic tool, and then there are many inductive invariants there. So, in fact, inductive invariants are of course, needed and very important, and we deal with them, this way. It's also possible to reason about them by symbolic reachability, and we have symbolic methods to do a search, but with symbolic expressions, using what is called the narrowing search. So that's another alternative to consider thinking about inductive invariance. But with these two tools, the invariant analyzer and the reachability logic model checker, then we can reason about inductive invariance. So this is much simpler. This is just making sure that your invariant, which need not be inductive, is actually satisfied by looking for a counterexample.
Okay, so the questions are piling up. So I'll let Subhash. So Warren, do you want to ask a question, Warren?
Oh, just in a sense, you mentioned something about an infinite states system, or your picture, I thought, and then then you also said the word model checking, and my mind broke right there. How do you model check an infinite states system in a sense?
Well, so you can do it in two different ways. One way is just you do bounded model checking only. So that's what many hardware companies do. But
they're doing it on a finite state system.
You do it in a finite state system. But you can do it in an infinite state system. And the reason for that is that the number of reachable states for each finite depth is finite.
I see. Okay.
And therefore,
how do you characterize a starting state then? I mean, there may be an infinite number of them. Is that also
that will be the second part of my answer. So
okay?
be a little patient with me. So I'm talking initially about explicit state model checking. So my first part of the answer is by explicit state model checking, you can still do bounded model checking when the number of reachable states is infinite, because as I said, the ones reachable at each finite depth is finite. And so if there is a counterexample, you will find it at some depth. And if the depth is within the bound, then bingo, you find it, right? But the other alternative, which I hinted at briefly, is that you can also do symbolic model checking, not in the BDD sense, but in the sense for infinite state systems in Maude. And the way you do that is exactly what you were saying. Instead of beginning with a concrete explicit state, you begin with a symbolic description of a set of initial states, for example, by patterns, perhaps also with constraints. And then you apply the rewrite rules corresponding to the transitions symbolically. That is to say, you don't do rewriting, you do unification. You don't do matching of a rule, but a unification. That's called narrowing. Narrowing in a completely different sense from the abstract interpretation meaning, Tom. It's just the words used in two different contexts. Okay, so you narrow with the rules, and then you can do an infinite exploration on an infinite state system, where the number of states may be infinite, symbolically, which in some cases happens to reach a fixed point. And then therefore, if you don't find anything after reaching the fixed point, then you're happy. So for example, if you have something like Lamport's bakery protocol, which the number of initial states is parametric and it's arbitrarily big, and so on, we can do that symbolic model checking of it, and then verify that mutual exclusion holds.
So just to
refine, but instead of doing explicit state reachability, we do the symbolic reachability.
Mm-hmm. Yeah. So just to refine that a little bit, imagine I'm sneaking up on all the numbers less than 5, and I get to, or let's say to 1, and so I get to a half, and then I get to 3/4, and then I get to 4/5, and 6/7, and so forth. And I'm sneaking up on there. How do you? I mean, can you show something like that? That will. It's sort of an infinite progression, but can you say something in your system that, by way of model checking, that will be less than 1 or something like that? Some continued fraction. You're wondering, you're exploring the continued fractions or something like that.
Well, so you can write rewrite rules that would explore these functions more and more, and then search for that.
I see. Okay, so you would use your math then. You wouldn't use the model checking algorithm that you just prove by normal.
No. I mean, I'm not sure I'm following the example in detail.
Jose, I can answer that if you want. I can answer that if you want. So this is actually related to one of the questions that comes up later. So there are techniques like this IC3, which can automatically generate the invariant for you. And the Zeno one, the one where you're converging, you're going 1/2, that's you're adding, say, 1 + ½ + 1/4 + 1/8, and you want to prove that it's always less than 2. Requires you to come up with an invariant. That is, the idea is that twice of what is left. The next number is all is always half of what is left. So that will allow you to prove that it's less than or equal to 2, less than 2 actually. So that kind of thing you can maybe do with IC3. There's a model checker we have called Sally, which can actually do examples like that.
Okay, I've said too much. Please go on to the next.
Yeah. So actually that brings up the next question, which is I think about do you have an implementation of IC3, Bradley's method, where you can automatically, or do you have any approach that automatically synthesizes inductive invariants?
You mean in Maude?
In Maude, yeah.
At the moment, not.
Okay. then there's a question. Sorry, I should let people ask them. Aaron, you want to ask a question?
Sure, thank you. So yeah, I'm interested in how you create compositions, I guess, of state spaces. I mean, traditionally you do this in object-oriented programming of objects, but like to reason about those objects formally, I guess you could use Maude to do that. I wouldn't know how though.
I don't know whether you saw lecture 3 or not, but lecture 3 is all about how you can model mathematically concurrent object systems made out of systems that have their own local state and communicate with each other through message passing typically. Those systems can have complex structure. The simplest one is a flat one where you just have a collection of objects floating in some kind of soup and sending messages to each other in some kind of ether. But it can be more interesting. You can have also what Caroline Tucker and I call Russian dolls. So you may have systems that where an object may self-contain many objects inside, which may self-contain many objects inside, kind of nested.
Yes.
Like that. And so, Maude allows you complete freedom to define different kinds of system structures like that, and then specify them and then analyze them.
And you could just as easily do for shared memory models.
What do you say?
Just as easily do this for shared memory as opposed to message passing. Yes,
yeah, right. There is a simple, there's a simple example today, which is not shared memory, but is something like that, where we're considering, modeling graphs as graphs, sets of pairs and not something else. So in Maude, you can just model graphs as graphs like that, and then there's a graph search algorithm. So a memory would be just instead of, so these are pairs of, in the simplest case is variable name and value, but otherwise you would have environment pairs, variable name and location, and then another set of pairs of location and value. So, modeling memory is just another concurrent data structure, like a set of pairs or something like that. So, and then you just model that. And so, yeah, and the whole rewriting logic semantics project that Grigori Rosso and I have been working on since the early 2000s does that for semantics of any either sequential or concurrent programming language. And you can model shared memory, whatever, or distributed memory, whatever you want.
Okay, thank you.
Right.
So, Jose, I have a question about the positive use of the kind of counterexamples, the search for counterexamples, which shows up, for example, in pathway logic and in the modeling of biological systems, where you really do want to find a way of getting from point A to point B. And this actually, in my speaking logic lectures, I mentioned how Claude Shannon had actually, was the first person to build such models as part of his PhD thesis, MIT thesis, in the 1940s. This was actually even before DNA was known. He anticipated that there would be something like DNA, and he went on to do this work. And so, Maude has been used a lot in kind of modeling biological and biochemical systems.
Right.
And, so the search for this same kind of search can then be turned into something that is actually positive.
Oh, yes, exactly.
Yeah. Can you say a little bit about that?
Well, yeah, so I can say something interesting about that, which is in the Maude book, we have this old puzzle of crossing the river with the goat and all this kind of thing, right? And so there what we do is
so that's the missionaries and cannibals problem.
Missionaries and cannibals, right? So what we do there is that we negate that situation and as a temporal logic formula, and then we get a counterexample of the temporal logic formula, which is a solution to the missionaries and cannibals problem. So the important point there is that temporal logic is, of course, universally quantified on paths. So when you find a counterexample, you find a proof of an existential quantification on paths for formula. So you go into CTL star, really. So that failures can be proofs, perhaps in a richer logic. In this case, a failure of a proof in linear temporal logic, which is universally quantified, become a counterexample for that becomes a proof for an existentially path quantified temporal logic formula in CTL star. So that's a good example. So many times you want to fail because failing is actually success.
Yeah, so actually, in that regard, I want to mention some other unpublished work of mine. So many years ago, Maria Soraya, who was my postdoc then, and I built something called a witness model checker. So it would actually, when you gave it a CTL problem, it would come back actually with a game that if you played against it, you would always lose. And that was the proof.
Right.
So the proof was actually given to you as a game.
Right.
And so that's something that is quite interesting about these things. That is, you can have these things where you play a move, then I play a move, then you play a move, and so if you think no, you should have found a path like this, then you can try actually inducing the system into that path, and you would always fail.
Right, but we can, just even without going to temporal logic, just something very simple like modal logic, we can give a meaning to the search command. In that, what the search command is doing is proving formulas. Let me see where I can write. Right here. It's proving formulas of the form that your system, so the canonical system for the rewrite theory and some initial state, satisfies some eventually P. That's what the search is proving. It's just a complete proof method for that. And so for the invariant, we are just looking for that. So we're looking for a failure of the invariant by proving instead of an always, or we prove an always I by showing that the eventually, so the invariant holds if this is false, if this cannot be satisfied, right? So the duality here, can be understood in terms of modal logic. The search, what is natively proving is eventually, eventually something will happen in the existential sense, which is the sense in modal logic, that possibly this could happen in the future, the possibly P. So that's what the search is doing, but then not possibly not P is always P, and so that's the way the proving an invariance is happening by the method I explained. So there is also just the search in finding the answer is just proving a possibly P property.
So that brings up another question which was in the chat. Robert, you want to ask it?
Yes, I was wondering about LTL and even more CTL support in Maude. So as an example, if I were to model a traffic light as just red, green, and blue or something, could I say like it will always become red after an orange without keeping previous color in the
yeah, you can say all this. Let me just thank you for your question. Let me give you a more complete answer to the kinds of temporal logic properties that are supported in Maude. So the most basic support is for linear temporal logic. which can be, there are two model checkers, one for explicit state and one symbolic, as I described, where you can begin with an infinite set of states described by a pattern. So there are two model checkers for that. There's also an explicit model checker for what we call the temporal logic of rewriting, which extends linear temporal logic also with action or event predicates. And this is extremely useful also to prove properties of systems under fairness conditions. And then furthermore, there are recently at Complutense University of Madrid, Maude has also been connected with external model checkers also for the model mu calculus and for CTL star. So through those interfaces, you can also use these richer logics as well.
Okay, and then we'll have one last question from Bob Robbins. Do you want to ask a question?
Yeah, thank you. So I'm mostly through lecture 3, and I was just wondering if you can confirm that I'm understanding it correctly. At my work, we're building a tool, and that tool is doing some optimizations through rewriting. But the rewriting is quite slow, and we also don't know if the rewrites are correct. Do I understand correctly that I could use Maude to both that I can use Maude both as a rewrite engine and also use it to prove these rules correct according to some semantics?
Yeah. So the thing is that Maude is not only Maude; it has also a formal environment in which you can do verification. Now, some verification can be done in Maude itself, like for example, the search command to verify invariants. The linear temporal logic model checker is also part of the Maude implementation itself. But other tools are in the environment. So to reason about your rewrite rules, well, we have a number of tools. For example, we have a tool to check in the case of rewrite rules that are used in a functional module for functional computation. Then having the Church-Rosser property or confluence is very important. So we have a tool to check that. We have tools to check termination. We have two tools to check sufficient completeness, meaning that you have given enough equations to fully define a function. You are not missing any cases in the definition of the function. So there is also an inductive theorem prover to verify properties of functional modules. And then at the level of rewriting logic, where you're just specifying concurrent systems, not just functional modules, then there are also these model checker tools that I mentioned, some inside Maude itself, some in the formal environment. And there are also deductive tools like the reachability logic theorem prover or the invariant analyzer. So this corresponds to a very basic idea that I mentioned also in the previous discussion session, which is that I always like to distinguish between two levels of formal specification. One level is what I call system specification, meaning defining a mathematical model of your system. That's what you do in Maude when you just write a Maude module. You build a mathematical model of the system, because Maude is not just, some engineering artifact that does something on a machine and changes states. It's a mathematical modeling language where each module defines a mathematical model in the sense of first order logic. So that system specification is not only a mathematical model, it's of course executable at the same time. But then once you have a mathematical model, then it makes sense to ask whether that mathematical model satisfies some properties or not. Otherwise, it doesn't make sense. You are talking nonsense. And so for that is that where you can have other logics that specify properties of that mathematical model. Okay, those logics could be Hoare logic, could be reachability logic, could be first order logic, with induction, could be many things. And so these tools in the formal environment, and some of them even in Maude itself, because like for temporal logic, allow you to then prove properties once you have done the first step, which is the system specification. So when you write something in some model in Maude, you are doing system specification, you are defining a mathematical model. But that is only the first step. And now the next thing is, what properties does my system have? And that, which was your question. Then you go to the formal environment, or sometimes to Maude itself, and then prove properties there.
Okay.
Thanks, Jose. Yeah, thanks
Okay.
again for the presentation. I think we've ended 2 discussions. We still have some labs to go, but thank you
Yeah.
for
Right. Okay. You're
great
welcome.
presentation and great stimulating discussions on
Right.
this. So thank you. And with that, we'll move on to the next speaker, the next discussion person, which is Natasha. Hi, Natasha.
Yes, hello. Hi, can you
Okay,
hear me?
so, yeah, we can hear you. We can see you. So let me introduce you briefly. So when I joined the University of Texas, one of the first professors I met was Professor Jim Brown, and actually ended up working for him my first summer in graduate school. And this was the experience of a lifetime. The late, great Jim Brown was an amazing human being. Warren was also mentored by him. And we all just remember him very fondly. He was an inspiration. And Natasha is one of his very distinguished students. She has been just a force of nature. She's been building open source SMT solvers, actually with a feature-rich things, using them in model checkers. She has led a highly productive group. So many of her students have actually gone on to careers with great distinction of their own. And I hope you will be similarly inspired by Natasha's work. Thank you, Natasha. Take it away.
Thank you, Shankar, for a very nice introduction. It's my pleasure to share some of my work and participate in this summer school. Yes, greetings from Switzerland, from Lugano. As you've seen my videos, so I start with the picture of Lugano, and let me just confirm it's true. So here's the view from my window. Can you see anything?
Mm-hmm.
Yeah, so this is Lugano, and this is our new building down there. So we just recently moved, actually, and very pleased to be here.
Yeah, I meant to say, Natasha, you work in paradise. I mean, for sure.
So yeah, so we would be very happy to see all of you. So one day, if you're ever in Switzerland, in southern part of Switzerland, where we are next to Italy, so you're always welcome to visit us and work with us as well. So I understand I don't have very much to talk about a lot. So, but I think maybe I will start with some slides, essentially doing something very quick to remind what it's all about, what I'm working on. So let me now, just a sec. Yeah. And then I will maybe give a brief overview of my first 2 lectures. And if you have questions, please ask. So I will just kind of start, some material, so you feel free to ask. So as Shankar told you, we actually quite active here. We are doing model checking, software model checking, and I was inspired by starting my research PhD studies at UT Austin. Alan Emerson was one of my co-advisors together with Jim Brown. It was a very nice collaboration. And then I also moved to Bell Labs. I worked with Bob Kurshan for a couple of years as an intern. My internship lasted 2 years though, so it was very successful. So I started really looking into problems of model checking software, because when I was a student, not so long time ago, but then mostly people were verifying hardware designs with model checking tools. and software was like untouched ground then. So we started trying and see what could be done. And ever since I was really into this topic, it brings a lot of open challenges, and it's a lot of engineering in addition to basic science. So yes, here in Lugano, I've been for the last 15 years. I moved here from Carnegie Mellon University when I received a career award, and I started focusing on actually a framework which not just doing one particular thing. So I would say that the innovation, so to speak, was to combine in the integrated manner model checking together with work on decision procedures. I observed through my experience as a student, as a junior researcher, that mostly it's never the case that these things are purely integrated. So people talk to each other. It's like different communities, different conferences even. So they use each other as black boxes, but they don't really have the opportunity to properly investigate the area of a complete integration. So I had this ambitious idea that why don't we try to do it? So I started a model checking track together with, at the same time, decision procedures track. Mostly because we had the luxury of having enough funding to have students working, and funded for a long time for these particular tracks. And we ended up by now having a number of tools which are quite practical. And I believe it's because we opened these black boxes and we managed to find solutions which benefit each other from both perspectives, from decision procedures perspective and the basic model checking algorithms. So we do have a lot of tools over the years. So here's the list of some of them. In this school, naturally, I don't have time to talk about everything. So I decided to focus on a couple. So namely HiFrog and UpProver. They share a lot of similarities in terms of the way how the symbolic abstractions of the systems are constructed. So it's quite easy to explain them together. But we do have other things. It's not only bounded model checking, which I will be talking here. It's also, for example, we have IC3 parallelized IC3 version and some other tools, which also benefit greatly from efficient decision procedures. If anybody has questions, feel free to contact us on other projects as well. So altogether, how we started actually integrating just basic model checking with decision procedures? Well, by means of constructing symbolic abstractions. So it's a well-known fact that if you just apply model checking directly to software, it's hardly possible to do anything reasonable. So it doesn't scale. There are way too many features which are very hard to model. And doing the approximated modeling and approximated reasoning is highly beneficial. But since we are in the model checking world where we aim at having everything fully automated, so we naturally looking for abstraction techniques which could be also be fully automatic. And one of the tracks we are pushing quite hard is the interpolation-based model checking. So we are having a large framework for computing interpolants, Craig interpolants, for various modeling logics. Which could be utilized for efficient symbolic reasoning when it comes to model checking. And HiFrog and UpProver are the instances where it really works quite nicely. I will, throughout my not lectures even, in the lectures it's already quite covered quite thoroughly, but we will also have the labs where we can demonstrate and let everybody to use these tools and experience firsthand how it pays off to have these symbolic abstract models to deal with model checking tasks. So as Shankar told you, so we do develop our own SMT solver. We call it OpenSMT. starting from almost like 13 years ago when we started OpenSMT. We decided it's to be open source. So we want people to use it, to contribute to it, and share with us their experiences. And it's been quite really successful. We have the reason why we develop it in-house is because, as I said, we want to make sure we have full control over it. Frankly, in the beginning, some people were quite skeptical. They were saying, why you would develop your own from scratch while you can go and get Z3 or CVC4. So at that time it was CVC3. I kind of agree with them, but is it what I said? Then it's a black box, and then I have to knock the doors and ask the developers to help me to adjust their tools for the needs we have. It works, but never works fully. So we decided, let's just have it in-house. We invested a lot of time into it and a lot of effort by many people. And so now it's a solid state. We have a revision 2, OpenSMT 2 these days, and it's quite competitive. So it has incremental features while doing the solving. So it's quite handy because it could be mapped to incremental verification when needed. So as I already said, it has this interpolating infrastructure, allowing us to compute symbolic abstractions using Craig interpolation procedures. And so it's parallelized. So for complex tasks, we have efficient search space partitioning techniques implemented. So it can be utilized whenever sequential reasoning does not scale. And yeah, it's efficient. We compete every year at the SMT competition. Occasionally we get some rewards for being successful. One of the recent results is a proof production. So we actually can certify that SMT solver is doing the right thing. So we have not done this yet, but potentially we are thinking of integrating it with model checking to guarantee that model checker also is actually doing the right thing, because all our tools are tools at the end, and you would like to have periodic checks, guarantees that the tool is actually doing the right thing. Not just the algorithm is correct, but the implementation of it is also right. So many tools are using OpenSMT, and as I said, Upprover and HighFrog are the very good instances. Here's our team. These are not a full group. It's only people who contributed to HighFrog and Upprover. And in fact, I would like to introduce to you my assistants. They will just connect very quickly. So it's Sepide Asadi. She is a PhD student here.
Yes, hello everyone. I am Sepide, a final year PhD student in Natasha's group, Informal Verification and Security Lab. I am mainly interested in software verification, and my research was particularly on the bounded model checking based on SMT solving. So during my PhD, I have contributed in the development of Upprover, which is an incremental bounded model checker for verifying different revisions of a C program. I also contributed in development of HighFrog, which is a DMC tool again, but for verifying a C program based on different technical algorithms such as theory refinement and summary refinement. So in the lab tomorrow and the day after, so I will be happy to assist you to get to know HighFrog and Upprover, and hopefully by the end of the lab, you will be able to verify your own program and write your own property and to enjoy it. I hand over to Martin, my colleague.
Yes, Martin Blicha is another PhD student in our group who is actively working on related topics to this project. So Martin, please.
Hi everyone, can you hear me? I'm Martin. I'm here for 4 years now, and I have been helping with the development of the tools that you will see, HighFrog and Upprover, and I'm also developing OpenSMT. I will be supporting Sepide with the labs. So if you have any questions, you can also feel free to ask.
So, and naturally, I would like to emphasize that we are having open positions for PhD studies. Feel free to contact us if you're interested to work with us. All right, so these are summaries of these two projects, HiFrog and Approver. So the complete information is our group website, so feel free to go there. So the underlying concept is BMC, bounded model checking. I believe you have been acquainted by now because several people already mentioned these topics. It's reachability analysis up to a particular depth. So it's a classical approach. And we are utilizing SAT and SMT solving to help us to perform these tasks. Even with the bounded constraints, so it could be not practical because the bound could be very large, the system could be very complex. So even with the use of efficient solvers, we still want to have abstractions. And the way both of our tools, HiFrog and Approver, doing the abstraction is the technique which we proposed a number of years ago. It's called function summarization. So we compute summaries, computational histories of the program, which could be reused in incremental runs to speed up verification and simplify the reasoning. So this summarization is fully automatic, and we are using Craig interpolation to help us to compute it. So overall, both tools allow different theory reasoning, and starting from Boolean encoding, and then since we employ SMT solving, we have different logics available for program encoding when we constructing the model of the system. So, and we have also an interesting infrastructure which allow us to decide on demand which reasoning, which logical encoding is most appropriate for modeling a particular problem we are analyzing, because naturally some logical encodings could be quite hard to deal with. They could be appropriate, they could be precise and quite expressive, but it could be bottleneck if you want to make sure verification succeeds effectively. So our infrastructure allows us to do adjustments and to start from some lazy encoding, something which may be not as precise as we would want to, but it could be relatively cheap computationally. And then if it proves to be not the right level of encoding, so it could be adjusted by appropriate theory refinements. It's one of the technologies we have. So, and this theory refinements actually done locally, only for the parts of the system where it's most appropriate. And this localization is enforced by the use of our summaries. So the summary is not just a nice way of doing the abstraction of the system, but they're also a nice way to partition reasoning and localize other techniques which help to adjust the precision of encoding and the effectiveness of the corresponding reasoning. So, and furthermore, both tools, since they're using Craig interpolation for constructing the summaries of the system, we developed a whole set of techniques which allow us to manipulate on the size and the strength of these interpolants, because it's quite clear that it depends. So sometimes you want weak summaries, sometimes abstractions, sometimes you want strong abstractions. It really depends on what task you're solver is, what your model checker is doing. And sometimes it's better to be loose, sometimes it's better to be very precise. And we do have an infrastructure which allows really to manipulate on this and adjust accordingly. So altogether, as I said, these two tools share the same background, but they differ in the fact that HiFrog is the incremental bounded model checker, which is designed to verify a single system against many, many different properties. So, and this is its goal. While AppProver is the tool which looks at various different systems. And what we observed, if there are systems which are closely related, like upgrades of the system or new versions or bug patches. So if we have systems like this, then our incremental bounded model checker AppProver really helps to re-verify these new versions of the system very effectively. So it really focuses on upgrade checking of the systems. So yeah, altogether, as I said, SMT is really tightly coupled. So here's the picture which in a very high level explains what we're doing. The tool takes as input a program written, for example, in C, together with the libraries which are required for the program verification. Then we have a number of properties to check. So usually in the C code, for example, this is assert statements. And we are checking reachability. We're doing reachability tests, trying to see if the assertions are satisfied or not. So this is safety properties. It's a classical encoding. So the model checker does a lot of intermediate internal steps by creating symbolic encoding of the program together with the property. It encodes into various first-order logics. And then using the solver to do the computation to see if the reachability is satisfied, if the bug is reachable or not. Violation of the property is the bug. And essentially, SAT solver, the complex task of state space traversal of the system is delegated to the solver now. And the solvers are highly engineered tools these days. They can handle formulas of very large sizes, millions of variables, millions of clauses, and they are able to be quite efficient. So if the solver returns us the formula, symbolic encoding together with the negation of the property is satisfiable, we know that the bug exists in the system, and the tool will report the counterexample and violation. Otherwise, if it's unsat, we know the program is safe. So this is a very high level representation. So here's some links. Well, first of all, of course,
so, Natasha, can we look at some of the questions that are there while people stare at the links? Yeah. So let me first, I guess, Mohammed, can you ask a question?
Yeah, sure. So do you hear me?
Yes, I do.
Okay, cool. So I think that the first thing was about, you mentioned that you are doing also the proofs for these tools, right? So the AppFrog and how do you call it? So,
AppProver.
yeah. So you mentioned that you are also doing proofs for them. So, and I was wondering that in which formalism are you proving that, or are you proving, like, for example, in Coq or something like that?
So let me clarify first. So I said that the OpenSMT, our SMT solver, is a proof producing tool now. And our future goal is integrated with the model checkers to have a proof certification for the model checking tasks. That has not been done yet. But on the SMT level, it's done. So we have a DAC paper 2021 with all the details about it. If you're interested to see, we suggested our own format, which is closely related, of course, to SMT2lib encoding and the proof in production formats used there. But we have our own variations, which we believe are most suitable for the proof production. So it's done there. So now we are certifying that the solver, SMT solver, is doing the correct thing.
So you mean that these proofs are complete, right?
Yep. So
Okay.
you can look up the data DAC, Design Automation Conference 2021.
Sure, thanks. And may I also ask that you mentioned about safety properties. Is it also possible to encode, or do you support also the security properties where we have, let's say, I want to check, for example, the memory bounds, or that it's memory safe and so on. So such kind of things, or an arbitrary behavior of an attacker, some things like that. Are they possible?
So that would require encoding of these properties. So to have an interface to specify the properties, so it could be then given to the model checker to get it analyzed. Like memory allocation and violation of the allocations is actually a default option for these tools. So if it's more complicated, some security policy, for example, which requires complicated formula to express it, it has to be instrumented and merged with the code. We do have a project from several years ago on verification of mobile programs, of the programs used in mobile applications, where various security policies have been verified. And we have such a tool which instruments security policies such that they can be mapped together with our symbolic models of the system and then be checked. So that's a feature. It's, but as I said, it's kind of an additional block which has to be added to Approver and HighFrog right now. So like by default, this block is not activated, but that would be possible. It has to be taken care. Somebody has to specify the security property appropriately.
Okay, right. And my third question was about the different tools that exist already. Like you already touched upon that idea that that from the beginning, your idea was to, if I understand correctly, so these are the black boxes, and you didn't want to be dependent on the developers, and you created in-house, and that is perfectly fine. So can you compare now the current state of your tools to the tools that exist? For example, I'm thinking about NUXMV, which supports bounded model checking. So can you maybe compare in some terms, like, and give us some idea when should we use, for instance, NUXMV, and in which cases or in what kind of scenarios your tool will beat this NUXMV, or the other way around? So can you please comment on the comparative status, current status?
So in the lectures, I believe in perhaps lecture 2 and lecture 4. So at the very end, when I'm concluding the material about the technology behind our solutions, there is some experimental data presented which compares our tools against the tools which are mostly related to our work. So for example, CBMC is the well-known tool for verification of C programs, is obviously a candidate to be compared against because our model checkers are also C model checkers. So you can see this difference there. So, and you can see that, for example, CBMC, the whole C prover framework does not use the computational histories which we are computing. So they very often simply lose. Well, for them, some problems which are quite trivial for our tools become really a major, headache. So this is the evidence. So we also compare to CPA checker framework. It's also popular and a lot of people using it. It does not do exactly reachability analysis, which our tools are doing, but on a high level, it's still related. So, and And you also can see, for example, when it comes to verification of different versions of the systems, that sometimes, since we can localize the change so effectively, and that our abstractions are quite handy, could be rechecked as opposed to complete re-verification of the system. So our tools really, really working very well. So we will, in our labs, demonstrate it. You will be able actually to understand these features, not only by watching my video lectures, but we will give you in assignments and some cases where you will be doing the job of the verifier, and we will give you a task not to do our our solutions, just basic model checking task. And then you will be using our tool with our extra features of summarization and abstraction and flexible abstraction. So you will see how beneficial it becomes to use it. So in this respect, you can really understand how it compares to the rest. The rest is just not doing it. And that's the whole point. But only the fact that we are having open white box SMT solver allows us to have these features. I believe other projects, unless they start really getting inside of the solver, would not have the algorithms which we have. So we have the decision procedures adapted, tuned with respect to the tasks we are doing.
Interesting.
So
Very,
Natasha,
thank you very much.
yeah. Natasha, related to that, actually, you happen to have answered Subhash's question as well. So, but related to that, can you say a little bit about how you trigger the lazy refinement? You said you refine both the theory and the strength of interpolation. So, how do you trigger the lazy refinement?
So here's one slide. I actually did not prepare to talk about theory refinement today, but if you give me a second, maybe I can, well, anyway, so I can explain here. So I have a slide somewhere, but it will take time to find it. So here's the infrastructure. Remember this very simple picture when I had a model check and SMT solver. So this is now I opening this box, it becomes a little bit more complicated. So, but you already see that I have, for example, summary refine box here. So what happens here when we do encoding of the system, so we can choose what level of abstraction in terms of encoding to choose. We can be, at the Boolean level, but could be at the level of different first order logics. So depending on our choice, we then start doing reasoning about verification of various properties. And while doing this reasoning, so our solver allows us to create a database. And here, if you see my mouse, so you see there is a database of summaries which we are computing for a particular theoretical encoding. So this, depending on the level of encoding, these summaries could be accurate or could be way too approximative. So we can start actually, if we realize during the verification that it was spurious behavior due to the approximations we made, we can start refining them. So, and the refinement is actually going to exploit again an SMT solver to help us to identify which part of the program of encoding or part of the formula was responsible for spurious failures. So it's a counterexample analysis. It's a traversal of the proof produced by the solver, trying to localize the failure parts, and then you start refining it. For example, you can just, for the fraction which you identified to be responsible for it, you can substitute it back to the precise encoding. Or you can choose a different level of encoding, but for that fraction. So it could be, linear arithmetics, or at some point, and then you decide to, to go to some other level of encoding, and that's, you do it gradually. That's how it goes. Yeah, I hope it's clear.
There's one more question about size of summaries. Robert, you want to ask that? That'll be the last question.
Okay, so I was looking in lecture 2 and 3, you're saying how you define these summaries and how you work incrementally But I was wondering what the size of those summaries are, and if you are keeping them around for the future, even if they don't hold now. So do you
All right, so I think, thank you, I understood. So let me start from the last one. So the summaries are being validated on each run whenever we have a new property to check, or we have a new system to check. So if the summary is detected to be violated, so there are some examples in the lecture notes. You can see them, like something can be broken and doesn't work anymore. So no, we don't keep it. So we just discharge it. So because we don't know if it's safe to be reused later. So we only keep summaries if we know that system is safe. So only safe system gives us sound approximations.
Okay, and what would be the sound of all the summaries together for a program the size, like if we were to prove things about GCC, how large would the summaries be? There's a lot of functions over there.
It's actually a very good question, because we have been investigating this. How could you measure the size of the summary? So our summaries are the interpolants, right?
Yes.
So, and the interpolants are the formulas, right? So you can count number of clauses, you can count number of variables, and the variables are different. Some of them have shared labels, some of them don't have shared labels. It's very technical. It really, with respect to the, you have to understand the interpolation procedure behind it. But this is the essence of it. So you can really measure it. So the easiest is like, just the size of the formula. And yeah, it's not that straightforward to map it directly to the source code. So because you're measuring a formula, yeah, but it's what we do. So in fact, we have our tool. Sometimes when we end up with very large formulas, we observe that massaging the formulas could be very beneficial, because you can reduce the size of the formula. Apparently, there are many redundancies in the formula created by the solver. The solver is doing its fantastic job trying to find the solution efficiently. But because of this, it's very often introduces a lot of redundant variables, and which the whole fragments of the formulas could be easily dropped and don't really affect the soundness. So we do have these massaging techniques that could be activated, and all this redundancy could be dropped. So we can actually make summaries compact if needed.
Okay. Then my very last question is, what is precision and efficiency? Could you give an example of making something more precise in the context of refinement?
So if you have Boolean encoding and you use the SAT solver, so it's bit blasting. So it's very precise, right? You exactly encoding every single fact. But it's will take enormous amount of computational resources to solve these formulas. So it's not efficient. So if you look at the demo, which my slides have, so in video number 1, so you will see with SAT encoding, with precise encoding, a relatively simple program, though it has some multiplication operations there, will take forever to be solved. We simply kill the procedure and abandon the effort. But if you have SMT encoding, so it's less precise, it's kind of approximative about what exactly is going in terms of the computation. So it's, yeah, less precise, but they could be much more efficient to be solved for a number of reasons. So, yeah.
Okay, thanks, Natasha. I think we should switch to the break now, and we'll come back. So, it's 9:17 now. So let's actually start at, 40 minutes past the hour for the labs. So we'll start the labs at 40 minutes past the hour to give people enough time to get a break. So we'll switch to the labs. I believe, today's labs are, let's see, Jose Meseguer and Tom Reps. So we'll have Meseguer at lab A and Tom Reps at lab B, starting at 40 minutes past the hour. Okay, I'm going to pause the recording and
Sorry, like
stop.
40 minutes or 40 minutes?